We left off with our discussion of biconditional statements that are represented by the double-ended arrow, the arrow in both directions. We will now continue. The truth table for P if and only if Q, shown in Table 6. Note that the statement P if and only if Q is true when both the conditional statement P if and only if P implies Q and Q implies P are true, and is false otherwise. That is why we use the words if and only if to express the logical connective, and why it is symbolically written by combining the right arrow and the left arrow. There are other common ways to express P if and only if Q. P is necessary and sufficient for Q, if P then Q, and conversely P if Q. The last way of expressing the biconditional statement, P if and only if Q, uses the abbreviation IFF for if and only if. Note that P if and only if Q has exactly the same truth table as P implies Q and Q implies P. Example 10. Let P be the statement, you can take the flight, and Q be the statement, you buy a ticket. Express the biconditional P if and only if Q as English sentence. Solution. You can take the flight if and only if you buy the ticket. Truth tables of compound propositions. Example 11. Construct the truth table of the compound proposition P or not Q implies P and Q. Rows. The number of rows in the truth table is equal to 2 to the power the number of propositional variables. In this case, there are 2 propositional variables, P and Q. Hence, there are 2 to the power 2 equal 4 rows. Columns. There are as many columns as there are compound propositions, propositional variables, and negated propositional variables. Construction. Complete the columns from left to right, moving from the simple to the complex. If we observe Table 7, we do P and Q, all possible alternatives, then we do not Q, then we construct the first compound proposition P or not Q, then we construct the next composition P and Q, then we construct the final composition P or not Q implies P and Q. Precedence of logical operators. Not has the highest precedence, then and, then or, then implication, then if and only if. Logical and bit operations. We associate with a binary digit, a bit, 1 with true and 0 with false. Definition 7. A bit string is a sequence of 0 or more bits. The length of the string is the number of bits in the string. Example, 1010100011 is a bit string of length 9. Example 13. Find the bitwise OR, bitwise AND, and bitwise XOR of the bit strings 011011, 0110, and 1100011101. We can see that the OR results in 111011 quadruple 1, and the AND results in 0100010100, and the XOR results in 1010101010. Now we proceed to do some exercises from our text that are similar to the exercises that have been assigned. You'll note that I put the solution in red. I do not want you to put the solution in red. I put the solution in red so that we can distinguish the solution from the exercise. Number 3, what is the negation of these propositions? Part A. Me has an MP3 player. We address this exercise in 3 steps. The first step is to mechanically apply the phrase, "It is not the case," to the original propositions. It is not the case that me has a MP3 player. Next, we apply our understanding of the English language in conjunction with our understanding of propositional logics to simplify our original statement. We remember that our statement is to be read not by a computer, by a mathematician who is presumed to be a human person. Thus, we write, "Me does not have an MP3 player." Finally, we format our results so they can be easily understood. Our proposition is in the left-hand column. Me has an MP3 player, and the negation we put in 2 cases. This is not the case that me has an MP3 player, and then we simplify to write, "Me does not have an MP3 player." Part B. There is no pollution in New Jersey. As before, we address this exercise in 3 steps. The first step is to mechanically apply the phrase, "It is not the case," to the original proposition. It is not the case that there is no pollution in New Jersey. Next, we apply our understanding of the English language in conjunction with our understanding of propositional logic to simplify our original statement. In particular, we note that our statement contains the double negative, not, no. We apply our understanding of well-written English to remove the double negative and write, "There is pollution in New Jersey." Finally, we format the results so that they can be easily understood. There is no pollution in New Jersey. It is not the case that there is no pollution in New Jersey. And finally, there is pollution in New Jersey. 10. Let P and Q be propositions. The election is decided and votes have been counted respectively. Express each of these compound propositions as English sentences. A, not P, the election is not decided. P or Q, the election is decided or the votes have been counted. Not P and Q, the election is not decided and the votes have been counted. Q implies P. If the votes have been counted, then the election is decided. Not Q implies not P. If the votes have not been counted, then the election is not decided. Not P implies not Q. If the election is not decided, then the votes have not been counted. P if and only if Q. The election is decided if and only if votes have been counted. Not P, not Q, or the quantity, not P and Q. Either the votes have not been counted, or else the election is not decided and the votes have been counted. Note that we were able to incorporate the parentheses by using the words either and else. 17. Determine which of these conditionals are true or false. Solution, Part A. If 1 plus 1 equal 2, then 2 plus 2 equal 5, and the answer is false. We write the original statement as it is given in the exercise. If 1 plus 1 equal 2, then 2 plus 2 equal 5. Since 1 plus 1 equal 2 is true, we have a true. Since 2 plus 2 equals 5 is false, we have a false. Putting both propositions together, we have a conditional statement. We have true implies false, and we know from table 5 that true implies false is false. Putting the foregoing together in a format that is easily understood. If 1 plus 1 equal 2, then 2 plus 2 equal 5. True implies false is equal to false. 31. Construct a truth table for each of the compound propositions. A, P and not P. How many rows do we need? Solution. The number, if the magnitude of P, the number of individual proposition variables, then we need 2 to the power P rows. In this case, we have only one propositional variable, P, and we need 2 to the 1 equal 2 rows. Of course, the title row making 3 rows. How many columns we need? Solution, we need as many columns as are required to construct the final expression one operation at a time. In this case, we need columns for P, not P, and P and not P, a total of 3 columns in all. And we see them below. P, true, false, not P, false, true, P and not P, all false. C, P or not P implies Q. How many rows do we need? Solution. If P is the number of individual propositions, then we need 2 to the magnitude of P rows. In this case, there are 2 propositional variables, P and Q, and we need 2 to the power 2, or 4 rows, and of course the title row, making a total of 5 rows. How many columns do we need? We need as many columns as are required to construct the final expression one operation at a time. In this case, we need columns for P, not P, P or not P, Q, and the quantity P or not P implies Q, a total of 5 columns in total. And we can see how we did this. First we constructed P, then we constructed not P, then we constructed P or not P, then we constructed Q, and finally we have the quantity P or not P implies Q. And that concludes our lecture.